we're looking at a web page here, and we're going to take a look at some CPU utilization while some of these things are going on. It's probably no secret to a lot of folks, but it's a bit of a mind bender to me. So without further ado, let's take a look at some of this stuff. All right, so here we have a web page, and yeah, it's got lots of ads on it, right? I was kind of interested, and I'm going to talk a little bit about this particular article, as a matter of fact. On a security-related note about how public-private networks on a partitioned router are capable of actually passing data back and forth through covert channels. And by covert channels, generally there are a couple of mechanisms, and this article talks about it, and it's very interesting. But as you see, this website, I'm not going to say anything bad about them, but you follow a link. I was sent this by a colleague, and started reading this article to understand it. And as you can see here, there's ads everywhere. I mean, there's ads on the top, on the side. Of course, you go down here, and you've got ads that are rendering themselves in the middle of the article. And of course, what's really irritating about that for me is you'll be scrolling down here. I'm going to read some more. Oh, and then I wait, and all of a sudden the text drops down to make room for this little pop-up. And then finally, as if that wasn't enough, let me get this browser window up into the view here. I got a little bit more. Okay. Yeah, as you can see here, not only do we have ads, so not only have ads at the top, we have ads at the bottom, we have ads on the side, we have ads in the middle. It's just ads, ads, ads. Oh my God. Now, the other thing that's very interesting about this, because and this relates kind of the subject of the article, is on covert messages. So I want to show you this. This is my CPU now. This is my CPU utilization while this page is running. You see something interesting here? I am pegged. This page is pegging my CPUs, and I'm on an i7, so I've got 4 cores here. And it is just going off like gangbusters. This is just amazing. Now, one of the ways of sending information, actually, is to create processes that task the CPU. And if you could do that in a regular way, well, you can see these peaks and valleys could be interpreted as ones and zeros, right? Potentially. Now, it's interesting subject in and of itself, but if you've got a bunch of activity going on, you've got some process which is actually trying to send information on this channel. As you can see, it's very noisy. So I guess maybe one of the pluses of having this web page loaded is there's a lot of noise in it, and that's going to reduce the amount of available space for actual intelligible information to be sent through CPU spikes. So this is an interesting subject. I actually had to pause what I was doing and realize that it's about time I installed ad blocker. Let's see what happens. So I'm on the page here, and I've paused it. Yeah, let's see here. So I've actually paused ad blocker on this page, and what we're going to do here is we're going to resume blocking ads on this page. Okay, and now we'll reload it. Now we've reloaded the page. And as we can see here, yeah, I don't have ads on the bottom, I don't have ads on the top, I don't have ads on the side. And as I read through this article, I don't have these nasty little things popping up that I could accidentally click on. And this is a much nicer experience. let's take a look at what's happening to the CPU right now. Okay. Huh. Well, look at that. Now, I sat and watched this thing for a few minutes after I turned that off. And now, and my CPU went almost completely quiet and my fans quieted down. So, if nothing else, it's just a real eye-opener as to how much these ads and all the crap that goes along with it, all the tracking, all the mouse tracking, etc. There's still analytics on this page, but I've now got a nice quiet environment. And now I can move over to a little demonstration of how we might create some covert information exchange, right? So for that, I'm going to try to bring this over here. And well, let's see, maybe we can, I've got the CPUs here all turned on. We'll do a summary view. No, I don't like the summary view. Let's turn that off. Let's show the graphs. Okay, so yeah, we got a nice summary view of the graphs here. And we'll try to keep an eye on that. Maybe make it a little, let's see here. Yeah, we're good. All right. So for this next trick, we're going to bring over this interesting web page as part of this article I'm reading. And try to bring this over the top. Now, the subject of this article has to do with the render cycle in React. So the premise here is that the difference between rendering components for purposes of comparing to the components as materialized in the DOM. So there's really two separate steps in React. There's a process of building up an internal representation of the component and then comparing that to a prior representation and saying, well, what's different? And I'm only going to make updates to the DOM itself, the actual page, that is based on the differences between the component from one point to the next. And in React, this is typically driven off of state changes. So state changes on a component, and it causes a reevaluation of the component. And then the component tree is traveled by React, and all this wonderful stuff happens. So there's quite a bit of computing that goes on just for that step alone. And in this case, this fellow, Chris Thorne, has written a very nice article that demonstrates how to set this up. And it's another interest of mine because this is an area of visualization. So visualizations tend to be, especially interactive ones, obviously, tend to be fairly high weight on the CPU. So what this does is we're going to watch what happens here. The CPU, I'll let it settle down a little bit. Okay, as I move here, it tracks my mouse and re-renders this chart component. Now, see what happens over here to the CPU. Just moving this slowly over the chart is causing that whole render process to be executed, and that's the subject of this article. How can we address this issue? But if I stop doing it, there you go. That's a pretty big bit, right? If I'm talking in source, if I'm going to send SOS, you know, did it did it. Let's try it. Did it. I'm just waving the mouse over here and making funny noises. But you can see I've got three fairly well identified peaks here in the right here. 1, 2, 3 peaks right there. It's probably a little better in the big form. There we go. Try to put this somewhere where it's not on the chart. Okay. There we go. Now, of course, if I want to send 3 dashes, I just need to stay a little longer on here. So this will be a dash. Now I've got a big high and wide spike there. Another dash. I'll just spend a little more time on it. So there's my dash. So it's easy here to produce pretty unambiguous pieces of information just by interacting with this application. So if you think about it for a moment, let's say I have, let's say this is an application which I'm logged on to, and I have some special rights on. So I'm in an admin role. Anybody else that goes to this page won't even be able to get to this component. However, I'm running other things on my system that are of lower trust. Could even be a web page, right? So the ability to sample CPU cycles or CPU utilization is generally a very low priority task without any security around it. It's just sort of something you need to do from time to time, and nobody gives it a second thought. But now, if you assume that this other application I have running over here is running such a sampler, it is now capable of doing a couple of things. One, it's capable of seeing potentially, if it's running as a process in the operating system, it's capable of seeing actually which windows are open. So it may be even the case that it can say, oh, when I see this this secured application being accessed, I'm going to start looking for activity. Now in this case, the activity would be the activity of the user. So the user wouldn't be sitting here sending messages necessarily. Although it's possible if the user is somebody who's acting as an agent and they need a way to send subtle signals. Well, here you go. Here's my Morse code generator right here on this chart. All I got to do is create little signals. Now, Claude P. Shannon wrote a pretty good book that everybody likes. On information theory, and basically it's all about sending bits of data over channels that have noise, how much throughput you can get on a channel with a certain amount of noise, etc. And this whole area of signal processing is a very interesting area, and it's useful for all sorts of things, including image processing, you name it, exoplanet discoveries, just simply reading the levels of light coming from a star as just a single value can be analyzed, and we can see whether or not that signal drops on a regular basis, and that this whole business of information theory is a really fascinating subject, and it's a key part of data science at the end of the day. So I just thought this was kind of interesting, something to keep in mind. And it kind of helps understand what this other article I was talking about was all about here. So in the case of, I got this React router network. Yeah, so router network isolation. Take this over to the side. Now, an interesting thing might be to see while I'm looking at this little web page here, I've got the ad blocker turned off and things are settling down a little bit. And we can you can look at this and you can tell me when you think I'm doing something somewhere else. All right, so I'm reading the article here, and another method through the address resolution protocol. So the other channel on this, so now you can see I'm obviously doing something somewhere. That CPU just went up. All right, over here, and So this is not so hard to understand in terms of that. CPU sampling is actually a pretty darn easy way to send information. And without too much trouble, using techniques from information theory, it's very easy to sort out the data, even on a noisy channel. So when this page is having ads run on it, I mean, this is all over the place. But if I do it long enough, if I send a bit of information over and over again, basically, it'll eventually come through the noise and be something you can analyze mathematically. They call it fast Fourier transform analysis. And that allows you to pull things out in terms of frequency rather than amplitude. So yeah, all of these spikes really could be represented as a waveform or a collection of waveforms, and some of those actually a collection of regular waveforms to be completely accurate. So any complex waveform can be built by the addition of regular sine waves at various amplitudes and various frequencies. Okie doke. So that kind of covers that. And the other aspect of this information back channel or covert channel. So this word channel comes kind of straight out of Claude Shannon's work, but the specific channels, there are things that happen over TCP that are done as housekeeping items, such as DHCP requests. Anytime we're looking for an IP address, we're going to be able to try to or obtain an IP address for use. We're going to generate this DHCP request sequencing that happens. Now the router in this case is responsible for providing DHCP services to its clients, to the client devices. And so this particular case is where the router is, now this is all software, kind of a software problem. It's not a TCP problem necessarily, but the router may be sending, hey, I don't recognize the network that you're looking at for an IP address for, so I'm going to send back hey, you're kind of nuts. And it happens to do that on both the secured and the guest unsecured and the secured networks. And so it's possible for somebody sitting over here on the guest network then to look for these specific NAC or DHCP denied packets. And we're also able to hide a little bit of information in the transaction ID number. That's interesting. Yeah. That's also kind of a similar thing that happens with group management protocol. And then there's the snap stuff, ARP requests, etc. So yeah, we can either do it by looking at CPU utilization, or we can look for these leaky packets that happen to be showing up on both networks as a consequence of some activity on the secured network. Now I haven't quite got into the timing based, but basically, yeah, this is where ARP comes in, and DHCP. You can also you can send ARP requests repeatedly, and again, so another just seeing a certain number of packets of a certain type in and of itself could be used to pass information. So it's a very interesting article. Okay, well, I think there's enough on that. And I think the next step here is I want to go over and take a look at the I'm going to shut this down. Actually, I had this up originally just to verify that, yes, indeed, rendering React components can be expensive. So, yeah, we see the number of renders skyrocket. So, every time the mouse moves, an event fires for our SVG, and the chart component updates its state. Now, I happen to have a little experiment of my own out here. And this is all just kind of wrapped around some of my interests in things like visualization. But we'll go over here to the Code Sandbox link for my website. And do a little playing around with the windows here. All right, there we go. Let's go to my sandboxes and go to our animation loop here. Let's move me over here for the moment. So this is a fun little program that just it's a pathfinding algorithm that I'd written just as a one of those 1 or 2 hours to kill things, and it originally been written in Python, and this output we're seeing was actually just generated as a nifty little console grid. But I thought, hey, it might be kind of fun to actually see the robot and do it graphically. So that's what this is. We can change the walls here, and we can see that the robot will wend its way through everything. And yeah, so this is also basically running a animation using, there's this an alternative to using set timeout as a way of causing the browser to render the page. This request animation frame mechanism essentially says call this callback when things are all quiet. When the screen's ready to update, and when the DOM's not being currently updated, do this in that interstice of time from one update to another. And then, of course, and then the general way of using it is to recall that recursively, so that you end up getting a loop going, basically. So this is very similar to the set timeout. I don't pretend to know all the ins and outs. Set timeout has some memory issues, and it also is not sensitive to when things are happening and other thread processes within the browser program itself. So apparently this is just a little bit better way of doing it. So I've actually been playing with this at a low level just so I can understand the mechanisms. Anyway, so yeah, that's my own little experiment. Actually, I'm just going to bring up the CPU analyzer, bring up the performance manager thing again here. I'll put it away. All right. Jump into the performance tab here. And let's take a look at CPU here while this is all going on. So I've got this set to a fairly low frame rate when I'm actually doing anything. And so this is not terribly heavyweight, as you can see. I'm not running hundreds and hundreds of objects or doing some sort of ray tracing or 3D scene rendering. So this is fairly quiet. Okay. But I will say, you can see here that the memory situation is not all that great. And that's something to keep an eye on. All right. Minimize that. So we'll put that away. So what we're getting at here, and that actually uses SVG as well. So SVG is nice. All the major browsers support it now, and because it's an element, page element syntax, it's very easy to instrument it and style it with HTML. And of course, React is in the business of rendering components, and so it's a very natural fit to React for visualizations. And there's a nifty little piece of code here that this just shows, yeah, we have an SVG tag, and then we have some higher level components here that are generating the other smaller bits of SVG, but that's what's going on in this program, just like mine was. All right. All right. So I'm just reading right along here myself to see if I can understand a little bit better what the issues are and maybe how we can mitigate them. So every time the mouse event fires, the chart component updates its state. So in the code here, you can see that this set state instruction every time the mouse location updates, and we've subscribed down here on the SVG component to the on mouse move event. So basically this is the callback. It's going to be executed, and so every time I move my mouse over the top of this chart component, this update mouse gets called, and every single mouse message results in a set state occurring. And as soon as we update the state of a component, that releases the hounds of React, and it says, oh, there may be something changed here. I'm going to have to look at the component. So that's what we're getting at here, and that's what we were seeing early on. Every time I move my mouse, that whole component tree is being reprocessed by React. It updates its state, triggers a re-render of itself and all of its children, and the underlying data we're visualizing isn't changing. So the actual outputs of these lower level components are going to be precisely the same. And therefore their DOM elements are not going to be updated. But we're spending a ton of time CPU-wise to determine that. So so this kind of defines the React component lifecycle. During an update, there is a should component update method, which will be called before the component is rendered. And if the return value of this method is false, our component won't be rendered. Now, we need to determine when the component should be rendered. Yeah, we always receive false, we won't see anything. So he's going to drop down into the axis and area components, I'm sure, and say, hey, we're gonna say for ourselves whether we need to be rendered, right? Current prop and next props in state. So a pure component base class that comes with a should component update. I have not played with this. This might be interesting. So we're going to do a little change here. We're going to extend pure component, and let's see what happens. Okay. So yeah, the initial setup, every component renders, so we get 4 render states. I'm going to pull up the performance counter now here. And I think we're going to see, not only just because he's, oh, well, would help to have it on CPU. All right, well, and we see here we've still got just 4 renders. It's way down here on the small. So nothing is re-rendering at this point, just purely by using that pure component implementation. Ah, that is very interesting. Yeah. I'm waving my mouse over the chart, However, I will say there's still something going on here, right? I mean, I'm still seeing kind of the same CPU behavior based on this, so it drops off fairly quickly. But I don't know. This is not doing anything for CPU that I can see, at least at a macro level. However, as far as React's concerned, it's not implementing any renders. But this is really what that is saying, is not implementing any DOM updates, since these components have the capability now to see if they've changed and sort of shortcut the process. So we've learned about React's lifecycle hooks, taken advantage of them, and we've saved, I think this is the part, we've saved precious CPU cycles on our users' computers. And I think the jury might be out on that. Huh. Yeah. I don't know. I'm kind of a data-driven guy, and as far as I can tell, that I'm just moving my mouse, as you can see here, and I'm still watching CPUs pegging here. Don't know about that. Don't know about that. Huh. Well, this might turn into another little article situation. Note to self.